All right, so today we're learning the product and quotient rules. I am doing this recording separately because I did it in class and didn't work out for some reason. So anyway, if you're not weren't in class today, you won't even know the difference, except there is no laugh track on this one. It's just me. So I can get through the notes a little bit more quickly. So today we're learning the product rule and the quotient rule. Before we start, though, just kind of some reminders. We have two functions now. For any given value of x, f of x is the y value machine, and f prime is the slope value machine. So if you think of a function like a machine, you can generate y values and slope values using f and f prime respectively. All right, so the first rule I'm going to give is the incorrect product rule. So this is not the way you want to do it. I give the incorrect product rule because this is the number one rule that I see students throughout the year, even after they've supposedly learned it, they keep messing it up. And they keep doing it incorrectly. So here's what I see them do. If you have the derivative of a product of two variable functions, f times g, the derivative is not as simple as just taking the derivative of both and multiplying them together. So in other words, the derivative of a product is not the product of the derivatives. It does not work that way. So the bad news is it's not that. The good news is it is something, and here's what it equals to. This is the correct product rule. The derivative of the product of two variable functions, f times g, it's going to be f prime g plus fg prime. F prime g plus fg prime. F prime g plus fg prime. There you go. Say it over and over again. So if you have two factors, you notice you're going to end up with two terms, and you're taking the derivative of each of one of them, but not at the same time. You're only taking the derivative of one of them per term. So f prime g plus fg prime. You can think of this extended to three different factors. Okay, the product rule, let's say we had three functions f, g, and h, and I'm not going to write the of x. But the derivative of f times g times h would be the derivative of the first one times the second two just get rewritten, plus now it's the middle one's turn, so it's f times g prime times h, and then finally plus the last one, f times g times h prime. So if you have three factors, you'll have three terms, and notice you only take the derivative of one of them per term. The other remaining factors just get rewritten. All right, let's try it again. The derivative, or not try it, again, try it. Again, if you want to repeat this before you move on, do so on your own. Press pause and then come back. F prime g plus fg prime, repeat. So I'm going to work example 1 as g of x equals x times 5x minus 3x squared. And I know I don't need to use the product rule in this one because I can distribute, but I'll do that at the end. I want to show you that the product rule actually works. If I take the derivative g prime of x, the derivative of my first factor is 1 times the second one just goes along for the ride, plus now the first one gets rewritten, and it's time to take the derivative of the second one using the power rule, which is 5 minus 6x. So you're done with the calculus there. If you wanted to simplify it algebraically by distributing, you get 5x minus 3x squared plus 5x minus 6x squared. And if you could combine things, you would end up with 10x minus 9x squared. So with the intent of expanding and collecting things on the end, if you get in the habit of doing that on the front end of the problem, simplify early and often, an ounce of prevention is worth a pound of cure, you can expand it and simplify before you even start. And you get 5x squared minus 3x cubed. Notice now it's just a power rule. We don't need the product rule. So g prime of x by the power rule alone would be 10x minus 9x squared. Okay, and that's exactly what we got down here. So we can take away, again, two things from this. First and foremost, when done correctly, the product rule actually works. Secondly, if you don't have to use the product rule, maybe you don't want to use the product rule. It's just another tool in your tool bag, tool belt, toolbox, wherever you carry your calculus tools. And sometimes it's too big of a tool for the job. If you simplify and then take the derivative in this case, fewer steps, fewer movable parts, fewer likelihood that you're going to make a careless mistake along the way. So keep that in mind. All right, so now we can combine the product rule with each of our rules, power rule, sine and cosine rule. This is the verb format. We read that as the derivative of that with respect to x. I'm going to go ahead and group those together. 5x cubed, I'm going to call my first factor. Cosine of x is my second factor. So now two factors means we're going to end up with two terms, one at a time. The derivative of the first factor I always take first. That's 15x squared times the second one gets rewritten. Plus 5x cubed gets rewritten times the derivative of cosine, which is negative sine. When you have a negative sign at the end, I like to put it in parentheses. If you put dot negative, that just makes my blood boil, because I guarantee you might come back to that and think that it's 5x cubed minus sine of x. So Don't put dot negative, put it in parentheses. Which now, if you simplify, you get 15x squared cosine of x. That becomes a minus 5x cubed sine of x. So if you can go straight from here to here, that's fine. Okay, I hope that with a little practice you can go straight to there and you won't have to rewrite. Now the question that I get in class a lot is, do we have to consider 5 as its own factor? And the answer is no, but you certainly can. Let me come off to the side here and show you something. If I had just had 5x cubed, we know that the derivative of that is 10x squared, and we're done with it. But notice you could elevate the 5 to its own factor. You can elevate to the status of having its own factor. And maybe on like elevate constant multiples to their own factor day, you do that, but on every other day you don't. If I use the product rule now with two factors, I should end up with two terms. So watch how it still works out. The derivative of 5 is 0 times the second goes along for the ride, plus 5 goes along for the ride, times the derivative of x cubed, which is 3x squared. And since 0 times anything is 0, 5 times 3 is 15, you still end up with 15x squared. And so notice up here when I called it 10x squared, you probably had some cognitive dissonance up there. I made a careless mistake, and it is actually 15x squared. So there you go. If you do things twice, you can always check your work. How about that? All right, so constant multiples do not need to be elevated to that status. You could just associate them with the closest variable factor. Over here, derivative with respect to x, we got two terms. Terms you could take derivatives independently. You can treat them as each their own problem. So now I'm going to add the grouping symbols in the first term. I have two factors, and the second term is just one factor. So I'm going to generate two terms from the first term with the product rule and one from the last term. So I should have three terms in my derivative. Here we go. 2 times cosine of x plus 2x now times negative sine of x. So that takes care of the derivative of that first term using the product rule. And I'll switch flavors here. Why not? Minus 2 times the derivative of sine is cosine. So once you expand it, now you can look to combine like terms. Those actually cancel, and you're left with negative 2x sine of x, a handsome little derivative. All right, product rule, product rule. Any questions? Pause it and try it again, or come see me in the morning. We're now moving on to the incorrect quotient rule. And very similar to the product rule, it says the derivative of a quotient is not the quotient of the derivatives. You can't just take the derivative of the top, derivative of the bottom, and divide it out. Even if you realize the denominators can't be 0, that doesn't work. But the good news is there is a correct quotient rule. And here it is. The derivative of f divided by g is gf prime minus fg prime over g of x squared. Now, unlike the product rule was just multiplication and addition. So it was kind of hard to mess that up unless you took the derivative of both at the same time. As long as you're taking the derivative of one term at a time, it doesn't matter if you do the first one first and the first one second because of the commutative nature of the operations. But for the quotient rule, it's subtraction. And subtraction is not commutative. So you have to take the derivative of the top one first. And because this one's a little bit more complex, we're going to do something here to make it a little more alliterative. We're going to call the top function the high function, h-i-g-h. But we're going to abbreviate it h over I. The bottom function is the low function, and we're going to call it LO, short for low. So we have the high over the low, the numerator over the denominator. Now we're going to take even more poetic license. Politics. Don't factor into math here. And we're going to change the low function to the ho function. So now we have the high over the ho, where the ho is the low. High over ho, the ho's in the bottom, the high's in the top. High over ho. If we then let the letter D stand for the derivative of, that's derivate, let me try to spell that again, the derivative of what follows, we could then change the quotient rule into what's known as the Ho-D-High rule. Ho-D-High rule is now the quotient rule. So here's what it says. The derivative of high over ho is ho d-high minus high d-ho over ho-ho, or ho squared, of course, where ho can't be 0. So if you say it real fast together, ho d-high minus high d-ho over ho-ho, ho d-high minus high d-ho over ho-ho. Press pause and say that 3 or 4 times to yourself real fast. Ho d-high minus high d-ho over ho-ho. All right, ho-d-high minus high-d-ho over ho-ho. It's not high-d-ho minus ho-d-high over high-high. It's ho-d-high minus high-d-ho over ho-ho. You start with a ho, you end with a ho. You got 2 ho's in the bottom. The ho's are lining up on the outside. Okay, start with a ho, end with a ho. Think 7 dwarfs. Hi-ho, it's off to work I go. That's where the hi-ho part comes in. But it's also like dyslexic Wilson from Home Improvement. He used to always butt into Tim's problems and say, "Hody hi, neighbor," at the end of the episode. Hody hi, he would say. Hody hi, neighbor. Okay? And then think of Santa who's not necessarily trying to get fit in the off season, but he's in a hurry. And a Santa who's in the hurry only says, "Ho, ho, gotta go. I can't say the third ho, you know." So he's just ho, ho. So Hody hi minus Heidi ho over ho, ho. Maybe you don't think of any of this thing at all. You just think of Hody hi minus Heidi ho over ho, ho. All right, so I start calling it the Hody hi rule, not the quotient rule. They are the same. Example 3. Let's try it out. Find the derivative of each of the following. You walk up to the problem, you're like, "What's up, problem? 4x minus 2 divided by x squared minus 1. You have the quotient of two variable functions. So now it's going to be the Hody hi rule. Don't forget the derivative of the all-important left side. The derivative of y with respect to x is either dy dx or y prime. Notation, notation, notation. And now we have ho, which is the bottom. D hi is the derivative of the hi function, which is 4. So there's Hody hi minus parentheses the hi function, 4x minus 2. D ho is 2x. Hody hi minus Heidi ho all over ho ho, or ho squared. So there's the calculus part. You're done. Now later on, we're going to be setting these things equal to 0, which means you're going to want to factor as much as possible. Right now, there's a common factor of 2 in the numerator, but that's probably hardly worth factoring it out. If you had a variable common factor, or especially a binomial common factor, you would want to factor it out of both terms right now before you expand. But in this case, the 2 is negligible. So I'm going to go ahead and distribute everything. Expand it out. You get 4x squared minus 4. Here's a common error, just to point out. You're distributing a negative from the left side and what is a 2x from the right-hand side. If you want to just tell yourself you're distributing a negative 2x, I've seen students kind of mess that up. So I'll just tell myself I'm distributing a negative 2x. And now I get a negative 8x squared and a positive 4x. Okay? I changed both signs, and I added an x and a 2 to each one of them. So be careful there. All over, not all of that over, just over the right side. All of that over x squared minus 1 squared. Now the bottom is already completely factored, so you wouldn't necessarily want to expand it. When you combine like terms in the numerator, then you're going to get a negative 4x squared plus 4 minus, or plus 4x, sorry, minus 4, all over x squared minus 1. If the top can factor anymore, you might want to factor it so you can divide something out. And again, once we set things equal to 0 later on, we're going to want to factor the numerator completely. So in this case, I'll factor out a negative 4, and I get x squared minus x plus 1 all over x squared minus 1. And I do not believe that the x squared minus x plus 1 would factor anymore into an x plus 1 or x minus 1. So anyway, this answer is considered simplified. This one up here, because nothing divided out, could be equally as simplified. So there you go. The algebra is really the heavy part after the derivative. The Hody hi rule is pretty quick, pretty easy. Just be careful with your algebra. Avoid careless mistakes. Take more steps rather than fewer steps when you're doing your algebra. All right. Letter B, we got f of x equals sine over cosine. That's a variable over a variable. So we can use the Hody hi rule. Here we go. The quotient rule says that f prime of x is ho, d hi is cosine, minus hi is sine, times d ho is the derivative of cosine is negative sine, and it's all over ho ho or ho squared. So remember, we write squared trig functions like that, cosine squared of x. So there's the derivative. The calculus part is over. Now it's up to a little bit of trig and algebra. We get cosine squared in the top. That becomes plus sine squared in the top, all over cosine squared of x. Now these do not divide out unless you split up the terms, but I don't think you want to do that anyway, because you got somebody slapping you in the face right there, and that is Papa, Pid. That's the Pythagorean identity number 1, and that is equal to 1. It's 1 over cosine squared. And of course, 1 over cosine squared is the same thing as secant squared of x. So now, anytime you ever see sine over cosine, you can just remember, hey, the derivative of that is secant squared of x. How often are you going to see sine over cosine? Well, quite a bit. If you remember, sine over cosine is just tangent of x. So what we've actually done right now is we have derived, appropriately enough, the derivative for the tangent of x function. The derivative of tangent is secant squared of x. So now you have 3 derivatives you need to know. The derivative of sine is cosine, The derivative of cosine is negative sine, and now the derivative of tangent is secant squared. You have a lot to memorize, and memorize as you go. The derivative of tangent is secant squared. All right. Let's jump to example 4 then, little application. Find the equation of a tangent line to this graph at x equals -1. So to write the equation of a tangent line, what we need, we need a slope and a point. We need a slope and a point. And all we have right now is an x value. So the point, since x is -1, it's going to be -1 comma f of -1. And the slope, that's going to be the slope at the point. That's going to be f prime of -1. So let's go ahead and find the point first, since we have the function. You plug in the -1 carefully for x, and you get 3 plus 1 is 4 over 4, so you get 4 over 4. So the y value is 1. Now before we can find f prime of -1, we need to find f prime of x. But before we find f prime of x, we need to be able to write that in a manageable form. It is a quotient, but the 1 over x is a complex fraction. So you can either multiply by x over x and get rid of the complex fraction, or do what I'm doing. I'm just calling 1 over x to the negative first. I know how to handle that with the power rule, so I'm going to leave it like that. But if you multiply by x over x, you kind of have nice little polynomials that you can work with instead. But either way, now I'm going to go to f prime of x. So make sure when you're going from f to f prime, you show it on the notational part on the left. Now it's ho. D high is just going to be x to the negative second. 0 plus x to the negative second. That's ho d high minus high. Make sure you put parentheses. They're your best friends in the math class. D ho is 1 all over ho ho or ho squared. Now, if you want to clean that up, it might help you evaluate it. I would recommend doing that with negative exponents or fractional exponents. You tend to think better without them. So be careful. Don't bring the x to the negative second all the way to the bottom of the main fraction. It just goes to the bottom of that term. X plus 5 over x squared minus 3 minus 1 over x. And if you distribute the negative, you got a plus sign right there. So that's kind of tricky too. So distribute the negative and write x to the negative first is 1 over x. And now it's positive all over x plus 5, quantity squared. So at this point, it's not worth multiplying by x squared over x squared to fix the complex fraction. The time to do that would have been in the beginning. I'm only going to evaluate it one time at a relatively easy number like -1. So I'm just going to leave it like that. So now we get 4 minus 1 is 5 minus 1 is 4 over -1 squared is 4 minus 3, and then 1 over -1 is -1. So there's your numerator, and the denominator is going to be 4 squared, which is 16. So that gives you 0 over 16, which of course is 0. Now 0 is a very interesting slope. That means we have a horizontal tangent line there. And a horizontal line, I put tangent, there we go. A horizontal line is of the form y equals some number. So you can write the equation pretty easily. If you know the y value that it passes through is 1, then that has to be the y value of the line. So the equation of the line is y equals 1. But let's say you don't want to do that. Let's say that you want to use Taylor form. You can do that. Here's the line in Taylor form. It's the y value of 1 plus the slope 0 times x minus the -1, which makes it x plus 1. So if it just tells you to write the equation of the line, you don't even have to simplify that. But of course, that second term goes away because it's 0 and you do end up with y equals 1. So nice little application. All right, example 5. I just want you to look on example 5. We're taking the derivative of an expression in both cases, and they're actually equivalent expressions if you look at them. They're just associated with factors differently. The left one has x times sine and then divided by x plus 1, whereas the right has x divided by x plus 1 and then times sine. They're exactly equivalent, but the way that they're set up, this one is going to be a quotient rule first and then a product rule inside the quotient. This one here is a product rule first and then has a quotient rule inside of it. So why would it matter? Well, it doesn't. You're just going to end up with two different forms of the right answer. Here's what I want you to realize. Later on, we're going to be taking the derivatives and setting it equal to 0. When you do the product rule, you end up with multiple terms. And when you end up with multiple terms and you're trying to set something equal to 0, if those terms have like denominators in them, you're going to have to get a common denominator first to get a single term so that you could then say the whole thing is equal to 0 and then the numerator could be 0 after that. So the product rule gives you multiple terms. The quotient rule is kind of a little bit better in my opinion because it gives you a single term. Its output is a single term. Now you may get more than one term in the numerator, but the whole thing is over g squared, so you get a single term. And when you set a single term equal to 0, you could then set the numerator equal to 0 right away. So just moving forward, if you have the choice to rearrange some factors so that you could use a quotient rule over a product rule, it might be beneficial. But let me show you what I mean. You walk up to the problem and you're like, hello problem, I see something divided by something. So it's a ho-de-hi rule. So here we go, the verb format. When you take the derivative, you don't put dy dx equals, the d dx just goes away. So you have ho, d-hi. Now d-hi is a product. So we're actually going to have to do the product rule now inside the quotient rule. So I'm putting a beefy brown bracket. It's the derivative of x, which is 1, times sine of x goes for the ride, plus x goes for the ride, times the derivative of sine, which is cosine. Close beefy brackets. So that's just ho d-hi. Now it's minus hi times d-ho, which is 1, all over ho-ho, or x plus 1 squared. So the brown part is the product rule inside the entire purple part, which is the quotient rule. And if you notice again, this is one term. It's huge in the numerator, but it's still just one term. In other words, we already have a common denominator. Whereas if you look at part B, if we do this one out of the box, now it's like, hello, something times something. This is a product rule. And in the first factor, when we take its derivative, I notice it's a quotient. So this would be a quotient rule inside of a product. So ho, d-hi is 1, minus hi, d-ho is 1, all over ho-ho, or ho squared. That's the derivative of the first, times the second goes along for the ride, plus the first now, x over x plus 1, times the derivative of the second, which is cosine. So notice here you have one term here, plus another term here. You have two terms now. And if you were to set this equal to 0, we would do it by getting a common denominator first so we can add the fractions. And once we had a single fraction, we could then set the numerator equal to 0. So keep that in mind. If you have an option, you probably want to do the quotient rule over the product rule, especially since I said in the beginning that the product rule is still the #1 rule that students tend to mess up. For some reason, the ho-de-hi rule sticks because I guess it's so fun. Ho-de-hi minus hi-de-ho over ho-ho. The product rule, they want to get in a hurry. They want to use the incorrect product rule. They want to take the derivative of both at the same time instead of doing one per term. Okay, so we've already learned the derivative of sine is cosine, the derivative of cosine is sine, and we just kind of stumbled across the derivative of tangent being secant squared. If you ever forget what the derivative of tangent is, you can call it sine over cosine and use the ho-de-hi rule. So now we're going to develop the others, the other three, the derivative of secant of x. I'll derive it here off to the side. All you have to do to define the derivative of secant of x is write it as a ratio using the reciprocal identity, 1 over cosine of x. Now you can use the ho-de-hi rule. Ho, d-hi is 0, minus hi, d-ho is negative sine, all over ho-ho, which is cosine squared. Now if you simplify that, you're going to end up with sine of x on the top, all over cosine squared. If you group one cosine there and another cosine here with maybe a 1, now you can associate these factors together. Sine over cosine is tangent of x. 1 over cosine is secant of x. So there it is. The derivative of secant is secant times tangent. And there it is written off to the side. So the derivative of tangent is secant times secant, or secant squared, and the derivative of secant is secant tangent. So they both have a secant in it. The tangent just has another secant, and the secant has another tangent. So you can think about it that way. They both have a secant, but then they have one of each of the other guys. Okay? Secant squared and secant tangent. Now, if you memorize those two, the other two come for free. Because as I mentioned earlier in the year, anything that starts with co or inverse co or arc co is going to have a negative derivative. So what's left? Cotangent, cosecant. Well, cotangent is going to be negative something derivative. Cosecant is negative something derivative. All you have to do is, since you're adding cos in front of these, cotangent, cosecant, just add cos in front of these. So because the derivative of tangent is secant squared, the derivative of cotangent is negative cosecant squared. And because the derivative of secant was secant tangent, the derivative of cosecant is negative cosecant cotangent. So again, you're just adding cos in front of both of those trig functions over here, and of course they are both negative. So memorize those four in conjunction with your sine and cosine derivative. You now have the derivative of all 6 trig functions memorized. Memorize them before you move on, okay? Don't try example 6 until you've memorized them. So hit pause, memorize them, and then come back once you have all 6 memorized. Okay, I'm moving on. Example 6. We're going to try out our new rules now. We can use the power rule, the product rule, the quotient rule, which is known as the Hody-High rule in this class. And now we have all 6 trig derivatives. So g of x is equal to x minus tangent x. Nothing needs to be rewritten. G prime is just going to be the derivative of x, which is 1, minus the derivative of tangent, which is secant squared. So there's a nice answer. But that looks a lot like a baby PID. So let's review the baby PIDs. 1 plus tangent squared was secant squared. That's baby PID number 1, as I call it. And 1 plus cotangent squared is cosecant squared. Kind of like what we just did there with the derivatives, except they're positive all the way through. So another name for 1 minus secant squared could be negative tangent squared of x. So that might be the multiple choice answer. On the multiple choice, I would have answer choices that would require you to maybe go 1 or 2 steps beyond where you normally would. For me, it's 1 less typing. I don't have to type in the number 1, so it's 1 fewer keystroke for me, and it's 1 extra step for you. So in math class, we call that a win-win, baby, from a teacher's perspective. All right, letter B, we got x times secant of x. We have a product now, x times secant of x right there. So the derivative of the left is dy dx, or y prime. I like dy dx now. The derivative of x is 1 times secant of x plus x goes along for the ride times the derivative of secant of x, which of course is secant x times tangent of x. And again, you're done with the calculus in 1 easy step. After that, since we might be setting it equal to 0, we would want to then factor things. And this one factors kind of nicely. It has a common factor of secant, which when you factor it out is 1 plus x tangent of x. That's what you're left with. So either one of these would be the final answer, depending on what you want to do next. And we'll stop right there for today. That takes us through example 6. So memorize your 2 new rules, product rule, quotient rule, and memorize these 4 new trig derivatives so that you have all 6 ultimately memorized. And we'll see you tomorrow.